looks like we're all good. So, pardon me. Welcome, everybody. Please, as you join today, let us know where you're coming from in the chat, wherever you're watching. We love to see it. I'm, of course, coming to you from beautiful downtown San Francisco, California, in the fragrant Soma neighborhood. Vi, where are you joining us from?
I'm here in Mountain View, not too far from you, Phil.
Just a stone's throw, as they say. And I believe Garcia also joining us from just a bit south of here, probably 20 or 30 feet away from you. Hello, Kolkata, Gig Harbor, Washington, Bhopal, India. Love to see it, folks. So, what we're doing on this episode, welcome, first of all, to OpenCV Tuesday Live. We're going to be giving you a step-by-step live video guide to soup to nuts participating in the bin picking challenge from OpenCV and Intrinsic, as well as our sponsors Orbic, University of Hawaii, and BOP. It's going to be a fun, very technical episode, and we will be recording this. It'll be available later on our YouTube channel for folks who maybe can't watch the whole thing. But I think now's a great time to get started. I think the best thing to do would be to say, welcome, Vi. Tell everybody what you got in store for them today.
Hello, everyone. Today, me and Augusta are going to show you how to prepare your submission for the bin picking challenge, how to submit it, and we're going to talk a little bit about the baseline solution that we provide for you. So the plan for today's webinar is the first 20 to 30 minutes we'll spend on the submission process. I'll talk about that like in probably 10-15 minutes, and then we'll have a quick Q&A for another 10 minutes. About how to submit your solution, how to prepare and submit it. And then the second half, Agastya will be walking through the baseline solution architecture, the inference code there, the training code, basically all the resources that we prepared for you to speed up your development process, basically. So I guess we can start, and I can start sharing my screen. Um,
Yeah.
all right. Let me know if you see my screen.
Yes, indeed. I see split windows here. Looks pretty good.
Yep, perfect. All right, so what I'm going to do here is I'm literally going to like go step by step through the BPC repo, and I'm going to talk briefly about like each of these steps. What exactly am I doing here, and why is it needed? For the beginnings, I have here the virtual machine, which is basically an empty virtual machine. It has an NVIDIA GPU, and we can confirm that the GPU is indeed here. It's a V100 GPU. I think this kind of GPU would be more than enough for the challenge. It's probably even a little bit of an overkill in terms of the power. And for the challenge, we do provide the evaluation instances we provide are, I think, based on L4s, which is 24 gigs of GPU RAM. So you have even more RAM for the challenge. Now let's just go through the repo here for this webinar. I'm going to use the baseline solution branch because I want to show you how to run the full pipeline, including the baseline solution. But you can also follow the steps from the main branch. They're mostly the same, except that you'll end up having empty solution instead of the baseline solution. All the other steps are the same. I'm going to skip now the overview and design steps, and I'll go through them in more detail while we're waiting for the dataset to be downloaded. And for now, let's just start from this like setting up section and just go through the setting up process together. I already have these apps installed, but just to confirm that, let's run these commands from here. You can see that I indeed do have Docker buildix installed. This is a separate plugin for Docker. I think it comes with the newest versions of Docker, but if you have older version, you need to install it separately. I'm also going to install again
Quick
the
note. Can you tap the hide button on that app.zoom.us is
Yep.
sharing your screen gimmick there? It's driving me crazy. Thanks, man.
Sounds good. So here, the next command I run is installing the 7-zip app. This is used to unzip the datasets. Now, finally, I also do have already the virtual environment for Python, but I'm just going to rerun this again. Now we have everything needed. The IPPC and Rocker CLI tools will install them during the configuration process. All right, now I'm literally going to run commands one by one from this tutorial. First, we just create the folder where we're going to have the data set, the virtual environment, everything is going to be configured. The repo, everything is going to be configured in this folder. We're also creating a virtual environment in this folder, a Python virtual environment, in which we'll be installing the IBPC tool. And we're activating this virtual environment. Now you can see that the virtual environment is activated. It's called BPC-env here. Next, we're installing the IBPC tool in this virtual environment. So the tool is called IBPC, but then whenever you need to call it from the CLI, you just need to call BPC. The problem is that BPC name was busy in PyP, so we had to call it IBPC. So this is the custom.
Sort of like import CV2.
Exactly. So this tool, this is a command line tool that we developed for you to simplify some of the steps. You don't need it to run any of the challenge steps, so you can do everything without this tool as well. It's just a small thing that we thought will be helpful for the participants to download the data, to run the evaluation locally, to do simple things like that. And also we've been, at least for the past few weeks, we've been constantly updating this tool. So please make sure to upgrade it every time you start working on this, to make sure you have the latest version of this tool. Now, the next step is to just clone the repo, this current repo we're looking at, and check out into the baseline solution branch. This is the branch I'm following here now. So we'll just run these commands and clone the repo. As you can see, the repo has been cloned and the branch currently is baseline solution. And the next step here is the first time we're using this BPC tool. It's called BPC Fetch IPD. It's going to download the part of the IPD dataset that you're going to need in the beginning. So here you can see it downloads 3 zip folders. It downloads IPD base, which just has the dataset structure essentially. It also downloads IPD models, which is the CAD models, and IPD val. Val is the validation dataset. I have the dataset open here actually. So as you can see, we're not downloading with BPC Fetch IPD, we're not downloading all the files. We're downloading only validation, base, and models files. You do need to use train dataset as well once you start training your models. And you may want to take a look at test dataset. This is the data, the test dataset is the data that is used to evaluate your submissions. But this is not mandatory. You can evaluate your submissions on validation as well. Validation is basically a small fraction the split from the test dataset. It has the complete same structure, dataset structure, all the same scenes, all the same objects, just less like the total captures, the total number of captured scenes is smaller. So the dataset itself is also much smaller. As you can see, it's just 6 gigabytes, not 150 gigabytes as the other datasets. It'll take a couple minutes to download and unzip the IPD val, but while it's running, just one small hint: if you want to download everything, not just the validation data set, but also the test and train and just like all the data that you have here, you can run BPC fetch IPD all. And we do have this mentioned here on the bottom. So this is the command that will let you to run everything and will automatically unzip everything into a single IPD folder, so that you don't need to separately download every file and then unzip every file. You can just run this once, wait for probably a couple hours, and you'll have all the data. And while also it's downloading and unzipping, let's just talk a little bit about the architecture of this repo and some of the reasons for the design decisions we made here. So we're using ROS to run the evaluations, and there are multiple reasons for that. But before I talk about the reasons, let's just talk about the general architecture. The goal of the participants here is to detect the poses of the objects in every single scene, right? And a single scene is basically a bunch of cameras capturing a number of objects attached to a robot arm. So you have, let's say, 3 instances of a single object, some gear, and you know the CAD model of that gear. You know that you need to be looking for that gear. I'll show you later how you know that. We passed the object ID that you need to be looking for every scene. And you have 3 camera images and 1 depth camera image from for every of these scenes. And you need to return us the poses of the objects that you detected in that scene. So that's the goal of this challenge. Now, in order to evaluate the solutions, as well as in order to be able to run your submissions later on a real robot, we decided to leverage ROS. And with ROS, your task is basically to build a single function inside one of these files that I'll show you in a second, and basically develop a service that will reply to the requests from a tester service. So on our evaluation instance, we'll have 2 services running. One is tester. It will basically be querying with the scenes, and the other is estimator. Estimator is replying with the detected poses. So your task is to implement a single function inside the estimator, as well as like all the models, training data, and the training code, and so on, separate from estimator. But in the end, you'll be submitting the estimator Docker image. Now, you don't really need to understand in detail how tester works. You don't even, in theory, need to run this locally. The reason we provide this whole for you is for you to be able to test your solutions before you submit, to make sure everything runs, nothing crashes. Because if you'll be able to run it locally, then the chances that it will run on the evaluation instance are extremely high. So this is for you to be able to test, and for like some transparency from our side for you to understand how the evaluation is running. So, but again, in the end, your goal is to implement this get pose estimates service, which is essentially a function inside the IBPC pose estimator.py. So here you can see there's this get pose estimates, and in the baseline solution, we already have some baseline implementation, which I'll go briefly through in a second. But essentially, your goal is to just add code here. All right, we have the data downloaded and unzipped. Now we're going to download the pre-trained models for the baseline solution, as well as the code from the baseline solution repo. So this was developed by our colleagues from Hawaii University, and I guess they will talk more about the architecture of this baseline solution. But for now, we'll just blindly copy it, clone it, download the data, and we'll just run it as is. So first, it's downloading the models into the models.zip. Once you'll be preparing the submission Docker image, this models folder will be included in that Docker image and will be uploaded with the Docker image, so that the models will be available for the evaluation pipeline. All right, models are downloaded, the repo is cloned. Now, the penultimate step here, we're just building the pose estimator Docker image. So again, this is the image that you'll be that you'll need to submit. And before you submit it, you need to build it to make sure all of your inference code is included, all your trained models are included. Basically, you have the full packaged solution. Building takes just a bit. It will be mostly done soon. And then once you have the image built, the final step here is just to test that that they can run a container based on your image that will be running and indeed responding to the tester queries. So we have this function built for you, again, to simplify some of your pipelines. It's called BPC test. And then here you put the name of your Docker image that you built. The name is not necessarily going to be this, you can change it. But then you just run this, and what this does is it downloads the BPC tester container, Docker image, and builds a container based on it. And we have all these containers pre-built for you here. So there should be a packages section somewhere here. Here, so we have the images pre-built for you. So in the current version, you don't even need to build the tester image anymore. You can just take it directly from the branch, from the repo. So once you run BPC test, it'll just automatically run all the necessary containers, including the containers that you developed, and it'll start the evaluation process. You can also see that it does some building during the start. The reason for this is that BPC test also includes the tool called Rocker, which allows us to add all the NVIDIA GPU support for your container after you build the container. So if you go into the Docker file for Estimator, you'll see that there is no NVIDIA Docker stuff here. Like we don't install CUDA, we don't configure NVIDIA drivers, nothing related to GPU in the submission container. And the reason for that is to simplify the development process a little bit. All the NVIDIA support is added during the container build-up based on the image you have. Now, this slows up a little bit the start of the container. So if you want, you can manually add the NVIDIA GPU configuration to your Docker file. It'll make the Docker image quite a bit larger, but then the starting of the container will be a little bit faster. But this is up to you. So for the purposes of simplicity, we have this like single command that you just need to run. And then once the pose estimator container finishes building, you'll have the tester querying estimator and estimator returning poses detected for every scene. Basically, you'll see something like this. These are just some logs printed from the baseline solution. It'll basically to tell us that the baseline solution is running. It's answering the queries. Once the tester goes through all of the scenes, it saves submission CSV file. It's a single CSV file that has all of your detections. And then this submission CSV file is evaluated on the in our evaluation pipeline. Again, you don't need to worry too much about this because all of this is done automatically. You don't need to do anything for this. But if you want to have like a single file that has all of the detected poses, you can check this submission CSV file. Oops, I think I have disconnected from.
Yes, the classic broken pipe. We've got a couple of questions here from the chat. First of all, from an anonymous attendee, they say if they downloaded the data set from Hugging Face, do they still need to fetch this data? Is that still, do they still have to do this step if they downloaded from Hugging Face?
No, but please make sure that the dataset you downloaded is the latest one because we've been updating the training dataset recently. So just make sure you have the latest version of the dataset. Otherwise, no, it's just going the same thing. It just downloads the data for you.
Perfect. Thank you for that. Another one here is inputs. It says inputs are 4 images from each camera, and the output is estimated pose result. Is that correct? They're asking.
Inputs are indeed for each camera. So we have 3 multimodal cameras that capture polarization and depth along with the RGB images. Or grayscale images in this case. And then we also have one depth camera that captures depth and grayscale images. So basically, you have 4 cameras in the scene, and images are for all these 4 cameras, and they're just positioned above these objects at different positions. But then the poses you need to return are with respect to the world coordinate system, and you can understand how the world coordinate system looks like by looking at the camera poses. If you do that, you'll notice that the world coordinate system is aligned with the Photoneo depth camera. So basically, in the end, you need to detect the poses with respect to Photoneo depth camera.
Great. Thanks for that. They would also like to know, another question here from YouTube was, are there any restrictions on stuff that can be used here? For example, people were asking about PyTorch or various other frameworks. Are there any restrictions on what frameworks can be used for this submission?
No. Plus, we highly encourage you to take a look at what has been already developed in the research community for pose estimation. And I think Agastya will talk more about that as well. But there are no restrictions like that as long as you can fit into the GPU memory and like the compute requirements in general.
Got it. Fantastic. And another question here about the cameras. Did we share the specifications for these cameras on the website?
Uh, what do you mean by specifications?
Uh, like the specs for the cameras themselves, like focal length and such like this.
Yeah, so camera intrinsics are available for each camera in each scene. There is a file in every of these folders actually. In tests, you have the intrinsics for the real cameras. In train dataset, you have intrinsics for the synthetic cameras that are used to render the training dataset. But yeah, basically all the camera intrinsics, camera extrinsics are fully available. All the camera images are undistorted, so you don't need to worry about distortion here at all. Um, yeah, I don't think there are any other specs you need to worry about.
All right, I think that's all the questions so far.
Perfect. So I'm just rerunning the test to validate that we'll have this running. In parallel, you can also take a look into the manual process of running all these components. So this is the substitute for BPC test command. Instead of running BPC test, you can manually run Zenarotor. Zenarotor basically makes sure the tester and estimator containers will find each other. Then you can run the pose estimator using Rocker, and then run the tester. So one important thing to note, I think, is that all these tools are tested thoroughly on Linux machines, and we've seen already that there are issues with Windows machines. I think everything here should work fine, except probably Rocker. Rocker may have issues on Windows machine. If that's the case for Windows machine owners, I would recommend just adding the NVIDIA config parameters to the Docker file, estimator Docker file, and then running instead of running this. Instead of running this, just run the Docker run for the estimator Docker file. That would be my suggestion. I think that way you can make sure you can develop this on Windows machine as well. All right, and while this is starting, I just wanted to briefly show you the details of the input and output information. So here in this example code, you can see that the input for your get pose estimates function is object IDs. These are the IDs of the types of objects you're looking for. So if you check the models, the IPD models Z folder, you'll see that there are 10 CAD models, and every CAD model has its own like ID name. So here we'll pass you which of these CAD models you're looking for in this exact scene. Then you have 3 cameras. These are RGBD polar cameras. And then you have 1 Photoneo camera. So these are the 4 cameras you're dealing with. And all of them have this camera class that is defined above. you can see this is also a helper class for you. It converts the ROS message into the Python class with poses, intrinsics, images, depths, and ALP, DLP for polarization. And by the way, while I'm talking about this, you can see that the evaluation process has started. So we have tester estimator communicating right now and poses being detected with the baseline solution. Now, again, your input is these 4 cameras and object IDs. And then your output is going to be a set of detections where every detection needs to be structured as a pose estimate message. And you can basically copy this code and reuse this code. If you just predict the detection pose as translation and quaternion for rotation, you can like directly reuse this code. Or you can also use this function rotation to quaternion, which converts the rotation matrix into quaternion. So just feel free to copy and reuse it, but this is how the submission in the end should look like, the response of the get pose estimates function. All right, so I think it'll take a little bit for these to finish, but while it's running, I'll just show you briefly how to then submit your solution. I'm not going to go through all the details of this process, especially since there is a token to configure, which is like personal for my account, so I'm not be sharing this token. But if you go to the submit tab of the challenge, you'll have the step-by-step instruction on how to submit your solution. For that, you just need to install eval.ai CLI tool, and then just run a bunch of commands one by one. I don't think there is anything you need to change except passing the name of the Docker image that you built. You just need to run these commands one by one, and that should be it. You'll have your submission done, and then you can see your submissions in the My Submissions tab. And once the submission is evaluated, you'll see yourself in the leaderboard. So you can see already there have been a few people who submitted the baseline solution. This is the metric that baseline solution will give you. And you can try it for yourself just to make sure the submission pipeline works for you. All right. Are there any other questions, or shall we proceed to the baseline solution description?
Let me do a quick check here over on our Twitch and YouTube. Looks like people are fairly quiet over there. Here in Zoom, we have one more question here. An anonymous attendee asks, could you show a sample demo for Git pose estimates?
What do you mean by sample demo? So this is the get pose estimates function.
Yeah, I'm not quite sure what they mean. Whoever asked there, if you could clarify in chat, we'll answer for you.
All right, or you can also reach out in Slack or the official forum, and we can answer asynchronically. And in the meantime, I guess I'll just pass the stage to Agastya.
All right, fantastic. I'm going to drop those links to the Slack and forum in the chat while we're here. Welcome, Agastya.
Hi, everyone.
A white hot ball of charisma as always.
Yeah, thanks. So what I'm going to show is the actual algorithm behind the baseline solution. So what Vahe went over was how you can submit a solution. What I'll provide is something that my lab at the University of Hawaii has worked on, which is a solution that shows you how to train a model for this problem and how to run it on the data set, and how to debug it a little bit. Now, the key things before we get into it is the problem we're trying to solve is pose from multiple viewpoints. The baseline solution is not a great implementation on purpose because we're trying to make sure that we don't bias the participants very strongly in one or another direction. That's why you can see the MAP is something like 0.01. We strongly encourage the participants to seek out either public repos or their own ideas for pose estimation. This is more just to show you what a simple solution could look like, and it doesn't have like particularly good performance. and I think that that's okay. So just to get started, here's the repository. It's called the BPC baseline, or the bin picking challenge baseline solution. Currently, there's 2 branches that are important. It'll all be merged into main within a day or 2. So we'll work on the branch that says blog, but this one contains a slightly better model and a much better description that walks you through everything that you need to know about pose estimation. I won't go through all of this, but I will go through it a little bit. But basically, this is what the baseline solution is able to do, right? It's given an image or multiple images of this object, it's able to estimate the pose. Now,
I guess I think you need to share your screen.
oh, am I not
Yeah, we're
sharing?
not seeing your screen there. It's all good.
Thought I did. My bad. Okay, can you see my screen now?
Yes, indeed. We can.
Okay, let me restart that part. So we have the baseline solution here at serplab/baseline, and we're going to the blog branch for this demo. This will be merged into main within the next day or 2. But this just contains a much better README with a lot more information. So the README here goes over every model along with some required information like, what is an intrinsics matrix, what is the projection matrix, etc. And then it also contains instructions for how to train each of the stages of the pipeline, how to verify your results, so on and so forth. So we highly encourage you to check this out if you plan on submitting something, but we also encourage you not to use the actual algorithm here, but to use an algorithm that either you create or a better one from the public domain, because this one is not great, and that's on purpose. But effectively, what this repository will do is, given 3 images of the scene, it will allow you to estimate the pose. Here are some examples. As you can see, the pose is not that accurate. The true object boundary is here, but the estimated pose is here. So clearly there's a lot of room for improvement. And this object is not detected entirely. So there's definitely room here. What the goal of this repository is how do we train on the BOP dataset? How do we test on the BOP dataset? How do we submit? And also some like basic algorithmic pieces you'll maybe use depending on how you do it. Another issue with this repo is we don't use the depth map. So this is just multi-view RGB. So there's some room for improvement there as well. I think it's pretty clear that depth improves pose performance. And then also this contains a bunch of baseline information. So with that, let's go ahead and actually show you what that would look like. What you would do is you would git clone the repository here, and then you can follow the README on how to download the datasets. So there's a download dataset, which I won't run because this takes about 25 minutes to download the training set. And also there's a Docker build command, both of which are in the README and both of which I've already run. So those are all available here in the README. Yeah, so the environmental setup. So what we'll start with is just running the Docker image that's already been built. So that would be here. Oh, sorry, this is not in the right place. So I have a copy of the repository that's already been built and everything is working. And I think the Docker image is already running, so I'll have to kill that. Okay, let's try it now. Yeah, and then you want to CD into the code repository. And so here you have all the code for training the models and running the models. What I'll do is I'll start by showing you how to visualize and run the models. So the pre-trained models are also available and they've already been downloaded as well, but the download instructions are in the README. So you should be able to download pre-trained versions of the models. And then to run the, I'll just open the README in here, I think. To run the Jupyter Notebook that I like to use for debugging, I like to do something like this, where this command is in the README. You can open the Jupyter Notebook, and then on your browser, you should get the following. And with this, there's an inference notebook. And the inference notebook here allows you to specify which test scenes, which models to use, so on, and it'll give you sample predictions. So let me see if I can just run it here. Yeah. The way that the model works is, sorry. So here you can see the updated results, and you can see here's the pose estimate from each of the viewpoints. You can change the scene number, for example. So instead of image ID 3, we could do a different image ID if you want to visualize a different image. And here you can see maybe because of the lighting, the model didn't get anything. Sorry, this is automatically closing the tab. Yeah. So you can look at different images, you can inspect the steps of the models, etc. We also provide like a visualization function that renders the pose on top of the scene so you can see how accurate it looks. Yeah. Any questions so far about how to set up the repository or how to run inference before I keep going?
I don't think so. I see Greg in the chat here says, I'm looking at the images. The objects are in a bin with a diamond pattern bin floor. Is this going to be common for images in this challenge?
Yes. I think so. The reason we picked a lot of these bins is because these are actually directly things that we've had to deploy in customer settings. So we chose these bins to be as close as possible to like real world industrial robotics problems. And this is actually nicer. Some of the bins that we've had have had like protruding things coming out that make it even more complicated.
That makes sense. I think that's all the questions we have right now.
Okay, then I'll keep going. So a brief overview of the pipeline is available in the blog post or in the README, but effectively, this is a 2-stage or 3 stages. Let me just find it here. So in the code, first what we do is we load the camera parameters. So I think someone asked like where are the camera specifications. So the function that we provide in the code load camera parameters will give you the K matrix and the extrinsics for all the cameras that you specify. And it will also give you the fundamental matrix between any two cameras, which gives you like epipolar lines. Then what we do is in each image, we detect a 2D bounding box around the objects with a YOLO model that we pre-trained. So I think this uses YOLO X. Once we have a bounding box from each image and the calibration parameters, we try to match the bounding boxes across the images using like epipolar matching. This is not ideal. I think there's better ways to do this, but this is just to show you that it's possible. So we simply check if one box lies on the epipolar line of another box. And if it does, then we consider that a match. And because we have 3 cameras, you can effectively just make sure there's a match in all 3 viewpoints. And then once we've matched the objects across the cameras, we triangulate the 3D locations based on the center of the bounding box. So if you have a center from multiple cameras and you have the calibration, you can then detect where the object is in 3D. This is super coarse, and this is one of the reasons the performance is not good. I think there's much better ways to get the 3D location of the object. We just triangulate the bounding boxes. And then we estimate the rotation with a separate rotation model that we trained, which is like a ResNet 50, and I'll show you how to train that as well. And once you have this, I think you can basically have the rotation, you have the translation from the triangulation, so you can just assemble the final pose. So I'll show you how to train both of these models. This is a quick overview of the pipeline. Each of these steps is again explained in more detail here with some key concepts. So for those interested, you can look in more detail. However, I strongly recommend using a different algorithm than the ones here because there's a lot of coarse things that won't give you the accuracy required to do well in this challenge. Okay, any questions about the steps in inference, or we'll just jump into model training? If there's no questions, I'll keep moving.
I'm not seeing any. I think we can continue here, Gustavo.
Great. So there's 2 models that you have to train. Each model is trained per object. So there's the YOLO X model that we have here. So I will show you the commands to this. You train in 2 steps. You run this command, which creates a YAML file that the YOLO model needs based on the Ultralytics repo. And then and your output will look like this. Then you can simply use the training script. YOLO trains very fast. We only train for about 30 to 40 minutes, and we noticed that it didn't really need more than that. However, I'm sure you can experiment how long you should train with in a Jupyter Notebook. Okay. And then to run training, I'll run this command. Oh, sorry. My local path is slightly different than the README, but if you start from scratch, you should just be able to use the README. So there's a tensor board as well that you can look at, but we probably won't get there in this. But, So you can see the training is started. I will kill it because we don't have time to train the entire network here. We also provide some sample code that you can use to visualize your YOLO detections on some training data. So you can look at this here, and based on that, you should be able to visualize the YOLO detections. Then there's also training the rotation estimation model. Now we offer 3 different outputs. You can estimate the rotations as Euler angles, as quaternions, and as a 6D rotation representation. So we support these 3 in the code, and the command to train that model is here. So this model takes a long time to train. Here we've defaulted to just 5 epochs because we figured people will want to debug first. But the pre-trained models we provide were trained on, I believe, 300 epochs. And we noticed this model is pretty poor in terms of performance. So I think there's some work here to improve that. But we can just start the training job, and it should work. Yeah, so you can see the training has started. Yeah, I think that's it. I think that should be enough to use the repository. I refer you to this for any more information. We have 15 minutes left. Are there any questions?
Yeah, we've got a few here in the Zoom chat from
Sure.
Kara Yang says, Augustia, can I use your environment accept estimation algorithm for this challenge?
Yeah, you can. In fact, we're hoping you will. The idea is that this will show you, and also you can extend the environment. So currently the environment is set up, I believe, with PyTorch 210, but we fully accept that participants might want to use TensorFlow or anything else. The environment is like the whole purpose of the baseline solution is to get you started as easily as possible, and so you spend the least amount of time on infrastructure and the most amount of time thinking about the algorithm.
Fantastic. Great explanation there. We've also got Aishwar would like to know, asks, could you elaborate more on ResNet for estimating rotation?
Yeah, so I strongly recommend you don't do this, but what we did do is basically we take the detected bounding box from each viewpoint and train a model to regress the rotation parameters of the pose. So the input is a crop that's resized, I believe, to 256 by 256, and the output is one of the 3 outputs that we offer. You can specify this when you train the model. So either it'll be like the 6D rotation matrix representation, the quaternion, or the Euler angles.
Thanks for that. Puneet in the chat. I'm not quite sure what they're asking here. I see they say, how many cameras do we need? Can we use a webcam or mobile camera? I'm not sure they're quite understanding the.
So we actually captured the images for you. The goal of the challenge is such that you do take the images that we have and get the best performance possible. So the baseline solution already downloads the data set, so you don't need any cameras to do this. The goal here is to focus on getting the best pose estimation algorithm possible. Does that answer the question?
I think you did. Great job. I'm looking over here on our YouTube and Twitch channels here. I'm not really seeing any additional questions. However, I think now would be it may be useful to
I
take a
think there was
look.
another question in the chat.
Oh, yeah, I see right here. It says, hi, Gustio, on which of the data sets should we train a model? There are 4 IBP dataset files in Hugging Face.
So you can train on all of them. That's what the code that we offer in the baseline solution does, but some datasets don't have every object, so the code in the Hugging Face will automatically subselect which training
So,
set to use. Go ahead.
Just to clarify on that, the zip folders on Hugging Face are sharded zip folders. So that means that it's actually just a single zip folder split into multiple files. So to get the training dataset, you need to download and unzip all 4. And then once you unzip, you'll see that there are quite a few scenes, I think 50 like subfolders there. And half of these subfolders have one set of objects, another half has another set of objects. In the dataset description, you'll see which subfolders have which objects. So you don't need all 50 to train for every object. For every object, you need just 25, where you can pick a subset of these 25. But you need to download all 4 zip folders in order to unzip them.
Got it.
I have a question actually to Agastya. Can you talk a little bit more about where participants can find some examples of good research projects?
That's a good point. So I'll post the link, but I think the easiest and best place is if you just go to if we Google I think BOP pose estimation challenge. I think this is a great place to find pose estimation algorithms. I think they have lots of publications that evaluate different algorithms. They have a leaderboard that you can look up.
Yeah, BOP is a great resource here. I'll drop these links both in the
talks
show
about a bunch
notes
of
and in the
different-
chat here as well.
Yeah. So I think looking at this could be good.
Yeah, and just for the participants, if you click different methods here, you can find very often papers on which these methods are based. And for some of these papers, you can also find GitHub repos with the code, with pre-trained models. So like it can be a great kickstart for you.
Yeah,
Most
for
of
example, here's someone's GitHub repo.
Yep. Most of these methods are also RGBD native, which means you can pass depth data along with the grayscale image here. And then you can adopt these methods to work for multiple viewpoints. You can adapt them to work with polarization information. So there's still some work you'll need to do. You can't just, or maybe you can just take the repo from here and submit, but that unlikely will give you winning chances. But at least this is like a great kickstart to get into like close to state of the art.
Yeah.
Fantastic. I think I'm checking our list of questions here. I don't see any further ones. I did just drop a link here in the chat for the list of frequently asked questions that we now have on the challenge page. There's quite a few that we've seen come up a few times, and so we've added them here. One that I just saw pop in over on Twitch is actually one of the FAQs, and the question is there a computational limit, a constraint for this challenge?
There is, yes. So inference time, total inference time for your solution has to be within 12 hours. And that's for about 1,200 scenes that we have in the test data set. So basically, you can calculate per scene, it's going to be like a few dozens of seconds at most. And then your solution needs to fit into 24 gigs of GPU RAM. And I don't remember exactly how much regular RAM do we have, but I think FAQ mentions that as well.
Yeah, I'm looking at the FAQ right now. It says 16 gigs of RAM, NVIDIA
Yep.
L4 class GPU with 24 gigs of GPU RAM, and the complete evaluation of 1,232 final data set within 12 Earth hours. Excellent. Aishwar, I hope I pronounced your name there correctly, in the chat says, do you have any recommendations of cloud virtual machines or for this challenge? Do you have like a sort of a list of if you were participating, where would you be looking? Because these can get expensive pretty quickly if you don't have the hookup.
Yeah, I would say most of the developments, like data loading and stuff like that, you don't really need a GPU, so you can save on that and just like run the simple CPU cloud instance just to do these kind of things to validate that code works. The GPU is needed mainly for training and then for validating your inference code. And there, usually what I was doing, I was just renting cheap GPUs on something like RunPod. There you can have, you can get the most basic one, I think a 4,500, something like that there would cost like 20 cents per hour or something like that.
Yeah,
And then,
RunPod's great. Also a big supporter of OpenCV and an OpenCV member organization. Thanks, RunPod.
yeah, and it's also a great service. Not an advertisement, so you can use other services as well. You can use like different cloud providers. It's just that whenever I was checking out different challenges, I was finding out that using RunPod is probably the easiest option. Another pretty good option actually is Colab on Google, where you can also develop everything without the GPU, but then once you need the GPU, you can just connect it to your notebook and then let's say run training code and pay only for the training time, not the environment setup time. So that's also quite useful.
Yes, that makes a lot of sense. They say Colab has a storage limit, which may be a problem here. Have you heard of this or run into this with this challenge by any chance?
I have not, but if people send more information into Slack or forum, we can take a look. What's the problem there?
Yes, and Kara in the chat again would like to know. I think we've answered this a couple times, but should I create my own model for pose estimation, or can I apply pre-trained models? The answer is yes. You can use pre-trained models. But maybe you want to implement your own.
Or fine-tune the pre-trained models. It's quite likely
Exactly.
you won't get the first place with the pre-trained models.
Yes, indeed. Any more questions out there, folks? We got about 4 minutes left here in the live stream, so get those questions in now if you want to ask them live. Puneet asks, is this session recorded? Yes, it will be available on the OpenCV YouTube channel. That's youtube.com/@OpenCVOfficial. I will drop that link in the chat for you now. That is where you'll find the recorded version of this live stream. It will be up, the recording should be up right after the show. So, and there's another question here, which I believe is on the FAQs page, which is, so we're the rankings. Basically, the rankings really begin with phase 2 here. The question is, to participate in the challenge, do they need to submit solutions for all phases? And the answer is yes. You need to participate all along the way from the challenge. You can't just jump in on phase 3. We won't accept those submissions. So I think that's about all we got for questions here. Any final thoughts or well wishes or whatnot for the audience out there, Vi?
Well, obviously, we wish everyone well. Please reach out to us with any questions. We try to respond to everything we see in Slack and in the official forum. I mean, I don't promise we'll spend a lot of time debugging issues with you, but if there is anything we can help with, we'll try to do that. So, and I also encourage everyone to stay active and also maybe publish their snippets of code that they found useful for their own purposes. Maybe some Jupyter notebooks that can do something useful for the challenge.
Yeah, it never hurts to share. I mean, it's obviously there's money on the line, there's stakes here in this competition, but I think there's a lot of little tools that will be required here that sharing those will probably make everyone's lives a little bit easier.
Yeah. Good luck, everyone.
Yeah. Gastya, any last words for the audience before we drop off this live stream?
No, good luck.
All right, yeah, good luck out there, everybody. As they said, if you have any questions that did not get answered here, please join the official Slack channel. It'll be in the show notes here with the Slack invitation link, or join the official forum. The link is also for both of those on the BPC Bin Picking Challenge website at bpc.opencv.org. We'll try our best to answer your questions there. You can also email us, newsletter@opencv.org, or competition@opencv.org might be better for this one, and we'll do our best to get you there. But we encourage you to ask your questions in public. That way, if anybody else runs into the same problem, they can easily find the answer, and we can help each other out. And keep it dry. Don't repeat yourself, as they say. Having said that, I think now is a great time to drop off here. Thanks so much for joining us, everybody, on this Tuesday morning. We will see you again on Thursday for our regular OpenCV live stream. Our guest this Thursday will be Adrian Lamb, who's running a super awesome AI hackathon here in San Francisco in the Chinatown neighborhood for high school students. And so we're really excited to see what they've got going on there. We will see you Thursday. Take care of yourselves out there. Take care of somebody else if you can. Best of luck in the Perception Challenge for bin picking, and have a great day wherever you may be.